Right now, somewhere in the constellation Sagittarius, 4 million solar masses of pure gravitational fury are devouring light itself. We call it Sagittarius A star, the supermassive black hole at the center of our galaxy. For decades, we've imagined black holes as cosmic vacuum cleaners with solid surfaces, like planets made of compressed matter. We were completely wrong about almost everything. The reality is far more disturbing than our intuition suggests. Black holes don't have surfaces in any way we understand the concept. They don't even have mass in the location you'd expect. What we're about to explore tonight will fundamentally change how you think about matter, space, and the very fabric of reality itself. The numbers alone are staggering. A black hole with the mass of our sun would have an edge smaller than Manhattan, yet contain gravitational forces so intense that time itself breaks down. Dr. Kip Thorne, the Nobel Prize-winning physicist who helped detect gravitational waves, calls black holes the most perfect macroscopic objects in the universe. But perfect at what exactly? Perfect at destroying our understanding of physics. Perfect at revealing the ultimate limits of matter and space. Perfect at showing us that reality operates by rules so strange they seem like science fiction. Tonight, we re-diving into one of the most mind-bending questions in all of physics. What actually is a black hole? Not what it does. We know it devours everything. Not where they come from. Stellar collapse is well understood. But what they fundamentally are at the deepest level of physical reality. Do they have surfaces you could theoretically touch? Do they contain mass in any recognizable form? Or are they something far stranger, tiers in space-time itself where our normal concepts of matter and surface cease to have meaning? The answers will take us through Einstein's most profound insights, quantum mechanics at its most bizarre, and recent discoveries that have Nobel Prize winners questioning everything they thought they knew. We'll explore the event horizon, that invisible boundary where escape becomes impossible, and discover why it is not really a surface at all. We'll investigate the singularity, where mass might not even exist as mass anymore. And we'll uncover why some physicists now believe black holes might be the key to understanding reality itself. You've probably heard that nothing can escape a black hole, not even light. But here's what's truly unsettling. According to our best physics, the mass that created the black hole might not even be inside it anymore. The surface you imagine touching would kill you long before you reached it. Not because it's dangerous, but because it doesn't exist in any meaningful way. Space and time themselves become so warped that our everyday concepts of surface and mass break down completely. This isn't just academic physics. Understanding black holes has led to breakthroughs in quantum computing, insights into the nature of information, and discoveries about how our universe might have begun. Some scientists now believe that black holes might be gateways to other universes, or even cosmic recycling centers where matter gets processed into pure information. If you're fascinated by the deepest mysteries of space and want to understand how reality works at its most fundamental level, subscribe and hit thumbs up. And here's a question that will blow your mind. If you could somehow survive the journey to a black hole's center, what would you actually find there? Comment below with your best guess. I'll pin the most creative answer that shows you really thinking about this. What we're about to discover challenges everything from Newton's laws to Einstein's relativity to quantum mechanics itself. We're not just exploring cosmic objects, we're investigating the very nature of existence. The boundary between matter and energy, between something and nothing, between what we can know and what might be fundamentally unknowable. Recent observations from the Event Horizon Telescope have given us our first actual photographs of black hole event horizons. But these images raise more questions than they answer. We're seeing the shadow of something that might not exist in any conventional sense. We're photographing the boundary of a region where physics itself might break down. By the end of tonight's journey, you'll understand why Stephen Hawking spent the last decades of his life obsessed with black hole paradoxes, why Einstein initially refused to believe his own equations when they predicted these objects, and why modern physicists are using black holes to explore whether reality itself might be a hologram, a two-dimensional information structure that only appears three-dimensional to us. The question of whether black holes have surfaces or mass isn't just about exotic cosmic objects. It's about the fundamental nature of matter, space, and time. It's about what happens when the universe's most basic rules are pushed to their absolute limits. And it's about mysteries that might hold the keys to understanding consciousness, information, and the deepest structure of reality itself. Now, let's begin our descent into the most mysterious objects in the universe, where even asking simple questions reveals how strange and wonderful reality truly is. Chapter 1. Phantom Boundaries. The first shock about black holes is that they don't have surfaces in any way you can imagine. When you think of an object, a planet, a star, even a soap bubble, you picture a boundary where inside meets outside. Touch a basketball, and your finger encounters resistance. The atoms in the ball's surface push back against your atoms. This is what we mean by a surface, a place where matter stops and empty space begins. Black holes violate this fundamental assumption about reality. The surface of a black hole, what physicists call the event horizon, isn't made of matter at all. It's made of warped space-time itself. Imagine trying to touch the surface of a rainbow or the edge of yesterday. You're trying to touch something that exists as a mathematical boundary, not a physical barrier. Dr. Leonard Susskind, one of the architects of string theory, describes it this way. The event horizon is like the surface of a river flowing over a waterfall. The surface isn't made of the water, it's made of the motion of the water. But even this analogy breaks down because the event horizon isn't made of anything moving through space. It is space, curved so severely that it creates a one-way boundary in the fabric of reality itself. To understand why this is so mind-bending, we need to appreciate what Einstein revealed about space and time. Before relativity, we imagined space as a stage where events happen, fixed, absolute, unchanging. Einstein showed us that space is more like a flexible membrane that can stretch, compress, and curve. Massive objects don't just sit in space. They warp the geometry of space around them. Picture a bowling ball placed on a stretched rubber sheet. The ball creates a depression, and if you roll marbles nearby, they follow curved paths around the depression. This is essentially how gravity works. Mass curves space-time, and objects follow the straightest possible paths through this curved geometry. What we experience as gravitational attraction is actually objects following the natural contours of warped space. Now imagine making that bowling ball more and more massive while keeping it the same size. The depression gets deeper and steeper. Eventually, you reach a point where the walls of the depression become so steep that marbles rolling past a certain distance fall straight down into the hole with no possibility of escape. This critical distance is analogous to the event horizon. But here's where the analogy breaks down completely. In our rubber sheet model, the bowling ball is still there at the bottom of the depression. In a real black hole, what happens to the original mass is far more mysterious. According to Einstein's equations, all the matter that created the black hole gets compressed into a mathematical point of infinite density called a singularity. But infinite density is physics code for our equations have broken down completely. The event horizon forms at a specific distance from the singularity, a distance called the Schwarzschild radius, named after Carl Schwarzschild, who derived the solution just months after Einstein published general relativity. For our sun, this radius would be about 3 kilometers. For Earth, it would be less than a centimeter. These numbers represent the size at which an object as gravity becomes so intense that space-time curves back on itself. What makes this truly bizarre is that the event horizon exists even when there is no matter there yet. If you could somehow compress the sun down to a 3-kilometer sphere, the event horizon would form at the moment the surface reached that critical radius. But the event horizon isn't the surface of the compressed matter. It is a feature of space-time itself, marking the boundary where escape velocity exceeds the speed of light. Recent computer simulations of black hole formation reveal something even stranger. During the collapse of a massive star, there's a brief moment when the event horizon forms before the matter even reaches the singularity. The star's core is still falling inward, but already the one-way boundary has appeared in space-time around it. You could have an event horizon with matter still falling toward the center, not yet compressed to infinite density. This leads to a profound realization. Event horizons are features of geometry, not matter. They're like the point of no return on a waterfall, not made of water, but defined by the flow of water. Similarly, event horizons are defined by the flow of space-time itself. Cross this boundary, and all possible paths through space-time lead inward toward the singularity. To make this concrete, imagine you're approaching a black hole with the mass of our sun. At a distance of 100 kilometers, space seems relatively normal. You could still escape if you had enough rocket fuel. At 10 kilometers, space is severely warped, but escape remains theoretically possible. But at 3 kilometers, the Schwarzschild radius, something fundamental changes in the geometry of space-time itself. At this boundary, the curvature becomes so extreme that all future light cones point inward. A light cone is a physics concept representing all the possible paths you could take through space-time starting from a given point. Outside the event horizon, your light cone includes paths that lead away from the black hole. Inside the event horizon, every single possible path leads deeper inward. It's not that something is pulling you in, it's that outward has ceased to exist as a possible direction. This reveals why the event horizon isn't a surface in any conventional sense. Surfaces resist. They push back when you try to pass through them. The event horizon doesn't resist at all. If you were falling through it, you wouldn't feel anything special happening. No impact, no barrier, no sensation of crossing a boundary. You'd only realize what had happened when you tried to turn around and discovered that back had become impossible. The mathematics becomes even stranger when you consider different reference frames. To someone watching from a safe distance, you would appear to slow down and freeze at the event horizon, your image red-shifting until it fades away. But from your perspective, you would pass through the horizon normally and continue falling inward. The event horizon exists differently depending on who's observing it. This observer-dependent nature of the event horizon has led some physicists to question whether black holes have well-defined boundaries at all. Dr. Ahmed Omhari and his colleagues have argued that the event horizon might be an emergent phenomenon, something that appears to exist only when viewed from outside the black hole, but has no reality from the perspective of infalling matter. Recent developments in quantum gravity have made this picture even more complex. Some theories suggest that what we call the event horizon might actually be a dynamic, quantum mechanical surface that fluctuates on incredibly tiny scales. Others propose that information about matter crossing the event horizon gets encoded on the horizon itself, like a hologram. What emerges from all this is a picture of black holes as fundamentally different from any other object in the universe. They're not things made of matter. They're configurations of space-time itself. The surface that defines them isn't a barrier you could touch, but a mathematical boundary where the rules of causality change fundamentally. Cross this line, and you enter a region where past and future, inside and outside, lose their familiar meanings. This raises the next obvious question. If black holes don't have conventional surfaces, what about their mass? Where exactly is all that matter that collapsed to form the black hole? As we'll discover, The answer challenges our most basic assumptions about what mass even means. Chapter 2. Missing mass. Here is where black holes become truly disturbing. The mass that created them might not actually be inside them anymore. According to our best understanding of physics, all the matter that collapsed to form a black hole gets crushed into a mathematical point called a singularity, a point of zero volume and infinite density. But infinity is mathematics' way of admitting it doesn't know what's really happening. Dr. Roger Penrose, who won the Nobel Prize for his work on black holes, describes the singularity as a place where physics comes to an end. Not just our current physics, but possibly any physics that operates with recognizable concepts like matter, energy, and space. The singularity represents the complete breakdown of everything we thought we understood about how reality works. To appreciate how bizarre this is, consider what happens during stellar collapse. When a massive star runs out of nuclear fuel, gravity suddenly overwhelms all other forces. The star's core, which might have been larger than Earth and contained more mass than our Sun, begins falling inward under its own gravity. Nothing can stop this collapse once it begins. Not atomic forces, not nuclear forces, not even the quantum pressure that keeps atoms from touching each other. In less than a second, all this matter gets compressed to nuclear density, the same density found inside atomic nuclei. At this point, matter as we know it ceases to exist. Atoms are completely destroyed. Even protons and neutrons get crushed beyond recognition. The material becomes a form of matter so dense that a teaspoon would weigh billions of tons. But the collapse doesn't stop there. According to Einstein's equations, if enough mass is present, even nuclear density isn't enough to halt the collapse. The gravitational field becomes so strong that it overpowers every known force in physics. The matter continues falling inward, past nuclear density, past any density that has meaning in known physics, until it reaches a mathematical point of zero volume. But here's what makes physicists deeply uncomfortable. At a mathematical point of zero volume, density becomes infinite. And infinite density is physically meaningless. You can't have infinite anything in reality. When your equations predict infinity, it means your equations have broken down. They're telling you that something fundamentally different is happening, something that requires new physics to understand. This is where the concept of mass becomes problematic in black holes. Mass, as we normally understand it, is a property of matter, a measure of how much stuff is there and how strongly it resists acceleration. But if all the matter in a black hole has been compressed to a mathematical point of zero size, in what sense does it still have mass? Some physicists have suggested that mass in a black hole transforms into something else entirely. Dr. John Wheeler, who coined the term black hole, proposed that matter might become pure geometry at the singularity. The mass doesn't disappear, but it stops being matter in any recognizable sense. Instead, it becomes curvature in space-time itself, a gravitational field without any material source. This idea leads to Wheeler's famous phrase, mass without matter. The black hole retains the gravitational effects of the original star, but the star itself has been transformed into something that isn't really matter anymore. It is as if the mass has been converted into pure gravitational field, a distortion in space-time that behaves as if matter were there, but contains no actual material substance. Recent theoretical work has pushed this idea even further. Some quantum gravity theories suggest that the singularity might not be a point at all, but rather a region where space-time itself breaks down into discrete units, quantum foam so chaotic that concepts like location and size lose meaning. In these theories, the original matter doesn't get compressed to a point. It gets dissolved into the fundamental structure of space-time itself. Dr. Carlo Rovelli, a pioneer in loop quantum gravity, describes it this way. The matter doesn't disappear, and it doesn't become infinitely dense. Instead, it becomes space-time. The atoms that made up the collapsing star become the geometry of space itself around the black hole. In this view, black holes are regions where matter has undergone a phase transition so fundamental that it stops being matter and becomes the fabric of reality. But the mystery deepens when we consider black hole thermodynamics. In the 1970s, Stephen Hawking discovered that black holes have temperature and entropy, thermodynamic properties usually associated with systems containing many particles. A black hole's entropy is proportional to the area of its event horizon, not its volume. This suggests that all the information about the matter that fell into the black hole is somehow encoded on the two-dimensional surface of the event horizon. This leads to the revolutionary idea that black holes might be holographic objects. Just as a hologram encodes three-dimensional information on a two-dimensional surface, a black hole might encode all the information about its three-dimensional interior on its two-dimensional event horizon. In this picture, the mass of the black hole isn't really inside the black hole at all. It is encoded as information on the boundary. The holographic principle, developed by Gerard 't Hooft and Leonard Susskind, suggests that this might be true for all of space-time, not just black holes. The three-dimensional universe we experience might actually be a projection of information stored on a distant two-dimensional boundary. Black holes become cosmic laboratories where this fundamental feature of reality becomes visible. But this raises even more disturbing questions about the nature of mass in black holes. If the mass is really information encoded on the event horizon, what happens when matter crosses the horizon from the outside? Recent observations have shown matter spiraling into black holes and disappearing across the event horizon. Where does this additional mass go? How does it get encoded on the boundary? Some physicists propose that infalling matter never actually reaches the singularity. It gets trapped just inside the event horizon in a region called the stretched horizon. In this picture, the matter is heated to enormous temperatures by the black hole's gravity and eventually gets radiated back out as Hawking radiation. The mass never really enters the black hole. It hovers just inside the boundary and slowly evaporates away. Other theories suggest something even stranger, that the interior of a black hole might not exist at all. The event horizon might be a kind of cosmic mirage, beyond which there simply is no there. In these models, asking where the mass goes is like asking what's north of the North Pole, a question that seems meaningful, but actually has no answer because it assumes a space that doesn't exist. Recent developments in quantum information theory have added another twist to this puzzle. Some physicists now believe that the mass in black holes might be stored as quantum entanglement, a non-local connection between particles that Einstein called spooky action at a distance. In this view, the mass of a black hole doesn't exist in any particular location, but rather as correlations between quantum states distributed across spacetime. The implications are staggering. If this is correct, then mass itself might not be a local property of matter, but rather a global property of quantum information networks. Black holes become windows into a deeper level of reality, where the distinction between matter and information breaks down completely. What emerges from all these theories is a picture of black holes as cosmic crucibles, where our most basic concepts about mass and matter are transformed beyond recognition. The mass that created the black hole doesn't disappear, but it might stop being mass in any sense we can understand. It becomes something more fundamental, pure information, quantum geometry, or holographic projection. This transformation reveals something profound about the nature of reality itself. What we think of as solid, material existence might be far more fluid and information-like than our everyday experience suggests. Black holes show us that even the most basic properties of matter, mass, size, location, might be emergent features of deeper, more abstract quantum processes. But if mass becomes so strange in black holes, what about their other fundamental property, their gravitational field? How can something with no conventional mass or surface still warp space-time so dramatically? The answer takes us deeper into Einstein's insights about the relationship between matter, energy, and the geometry of space itself. Chapter 3. Gravitational Ghosts. Here, as perhaps the most mind-bending aspect of black holes. They can have enormous gravitational effects without containing matter in any location you could point to. A black hole with the mass of 10 billion suns, like the one recently photographed in Galaxy M87, warps space-time so severely that it affects objects thousands of light years away. Yet all this gravitational influence might originate from a mathematical point containing no actual matter, or from information encoded on a distant boundary. This violates everything our intuition tells us about cause and effect. In our everyday experience, forces have sources. Push a book across a table, and your hand is clearly the source of the force. The book moves because matter in your hand physically interacts with matter in the book. Gravity seems similar. Earth attracts objects because Earth contains matter, and that matter somehow reaches out to pull things toward it. Einstein shattered this intuitive picture completely. In general relativity, gravity isn't a force at all. It's the curvature of space-time itself. Massive objects don't reach out and pull on distant matter. Instead, they warp the geometry of space and time, and other objects simply follow the straightest possible paths through this warped geometry. What we experience as gravitational attraction is really just objects moving along the natural contours of curved space-time. This geometric view of gravity makes black holes even more mysterious. If gravity is just curved space-time, then black holes are regions where space-time has become so severely curved that it folds back on itself. The gravitational field of a black hole is unproduced by matter at the center. It is a feature of the geometric structure of space-time throughout the entire region around the black hole. Dr. Kip Thorne uses a powerful analogy to explain this. Imagine space-time as a vast sheet of rubber. Normally, this sheet is relatively flat, with gentle curves around stars and planets. But at a black hole, the rubber sheet develops a deep, funnel-shaped depression that extends over a vast region. The gravitational effects we observe are uncaused by something sitting at the bottom of the funnel. They were caused by the shape of the funnel itself. This geometric interpretation leads to a startling realization. A black hole's gravitational field exists even in regions where there's no matter at all. The empty space around a black hole is curved in such a way that objects placed in this space naturally fall inward, even though there's nothing material there to pull them. The curvature of empty space itself creates what we experience as gravitational force. Recent calculations by theoretical physicists have pushed this idea to its logical extreme. Some models suggest that you could, in principle, have a black hole solution to Einstein's equations with no matter anywhere, not even at the center. These vacuum black holes would be pure gravitational fields, existing as stable configurations of curved space-time without any material source whatsoever. The mathematics behind this is surprisingly elegant. Einstein's field equations relate the curvature of space-time to the distribution of matter and energy. But the equations are nonlinear, which means the curvature itself can act as a source of additional curvature. In regions where space-time becomes severely warped, the curvature can become self-sustaining, maintaining itself even without any material source. Think of it like this. Imagine a whirlpool in a river. Normally, you need something to create the whirlpool, a rock, a stick, some obstacle in the water. But under certain conditions, the flowing water can create stable vortex structures that persist even after the original obstacle is removed. The whirlpool becomes self-sustaining, maintained by the motion of the water itself rather than by any external object. Black holes might work similarly, but with space-time geometry instead of flowing water. The curvature becomes so extreme that it creates a self-sustaining gravitational structure. The black hole mass isn't located anywhere in particular. It's distributed throughout the curved geometry of spacetime itself. This idea receives support from recent work in numerical relativity, computer simulations of Einstein's equations. When physicists model the collision of two black holes, they find that gravitational waves carry away energy and angular momentum. After the collision, the resulting black hole has less mass than the sum of the original two. Where did this missing mass go? It was radiated away as pure gravitational energy, curvature in spacetime that propagates outward as waves. This demonstrates that mass in black holes isn't conserved in the way we normally understand mass conservation. The mass can be converted directly into spacetime curvature and radiated away. What we call the mass of a black hole is really a measure of how much the black hole curves spacetime, not a measure of how much matter it contains. The implications become even stranger when we consider Hawking radiation. According to quantum mechanics, the vacuum of space isn't really empty. It's just filled with virtual particle pairs that constantly pop into existence and annihilate each other. Near a black hole's event horizon, the extreme curvature of spacetime can separate these virtual pairs, causing one particle to fall into the black hole while the other escapes as real radiation. This process slowly reduces the black hole's mass, but in a way that seems to violate our understanding of where mass comes from. The Hawking radiation carries away energy, which corresponds to a reduction in the black hole's gravitational field. But this energy doesn't come from matter inside the black hole. It comes from the structure of spacetime itself. The black hole is literally evaporating its own gravitational field into radiation. Dr. Dompage, a former student of Stephen Hawking, calculated that a black hole with the mass of our Sun would take longer than the age of the universe to evaporate completely through Hawking radiation. But smaller black holes evaporate faster. A black hole with the mass of a mountain would explode in a brilliant flash of radiation in less than a second. In these explosions, all the black hole's mass gets converted into pure energy and radiated away. What happens during these final moments of evaporation reveals something profound about the nature of mass in black holes. As the black hole shrinks, its event horizon gets smaller and smaller. But the gravitational field doesn't just fade away. It gets converted into radiation with surgical precision. Every bit of curvature in spacetime around the black hole eventually transforms into escaping photons and particles. This process suggests that what we call the mass of a black hole is really stored as information in the geometric structure of spacetime itself. The black hole doesn't contain matter in any conventional sense. It contains curvature. And this curvature can be converted back into matter and energy when the black hole evaporates. Recent developments in string theory and loop quantum gravity have provided additional support for this geometric view of black hole mass. In these theories, what we call matter at the fundamental level is really just different ways that the underlying structure of spacetime can vibrate and fold. Black holes represent regions where this geometric structure has become so highly organized that it appears to us as concentrated mass and gravitational field. Some physicists now describe black holes as gravitational crystals, highly ordered structures in spacetime geometry that persist like crystals persist in matter. Just as a salt crystal is a stable configuration of sodium and chlorine atoms, a black hole might be a stable configuration of spacetime curvature that maintains its structure through purely geometric processes. This geometric interpretation of black hole mass leads to a remarkable conclusion. The most massive objects in the universe might contain no matter at all. They pure gravitational field, distortions in the fabric of spacetime that behave exactly as if they contained enormous amounts of matter, but actually contain only information encoded in the curvature of empty space itself. Understanding this geometric nature of black hole mass opens up profound questions about the relationship between information and gravity. between geometry and matter. If mass can exist as pure space-time curvature, what does this tell us about the fundamental nature of matter itself? And if black holes are really geometric objects rather than material ones, how do they process and store information about everything that falls into them? Chapter 4. Information Paradox. The deeper we probe black holes, the more they challenge our understanding of information itself. In 1975, Stephen Hawking discovered something that still keeps physicists awake at night. Black holes destroy information. Not just the information written on a piece of paper that falls in, but the quantum information that defines the fundamental state of every particle in the universe. This discovery created what is known as the information paradox, a conflict between general relativity and quantum mechanics so severe that resolving it might require rewriting the laws of physics. To understand why this is so disturbing, you need to appreciate that information conservation is one of the most sacred principles in physics. In quantum mechanics, the information describing a system state can never be destroyed, only transformed. Learn a book, and while the words become ash and smoke, the quantum information describing every atom's position and state still exists. It's just been scrambled into an apparently random form. In principle, if you could track every particle perfectly, you could reconstruct the original book from the ash. This principle, called unitarity, is what makes quantum mechanics predictable despite its probabilistic nature. Even though individual quantum measurements are random, the underlying information evolves deterministically according to Schrödinger's equation. The universe maintains a complete record of its quantum state at all times, even when that information becomes practically inaccessible to us. Black holes seem to violate this fundamental principle. When matter falls past the event horizon, it appears to disappear from our universe entirely. According to classical general relativity, this information travels to the singularity, where space-time curvature becomes infinite and physics breaks down completely. The information that described the infalling matter seems to be destroyed along with the matter itself. But Hawking's discovery made this problem much worse. He showed that black holes emit thermal radiation due to quantum effects near the event horizon. This Hawking radiation is completely random. It contains no information about what fell into the black hole. A black hole formed by collapsing hydrogen atoms would emit exactly the same radiation as one formed by collapsing Shakespeare's complete works. The information that distinguishes these scenarios would be permanently lost. As the black hole evaporates through Hawking radiation, it eventually disappears entirely, taking all the information that ever fell into it to complete oblivion. This process would violate unitarity on a cosmic scale, destroying information that quantum mechanics says must be conserved. It's as if the universe develops holes in its memory, losing track of parts of its own quantum state. Dr. Leonard Susskind recognized that this paradox strikes at the heart of how reality operates. If information can be destroyed in black holes, then quantum mechanics itself might be fundamentally wrong. The equations that successfully predict atomic behavior, chemical reactions, and quantum computers might all be approximations that break down when gravity becomes extreme. Alternatively, Einstein's general relativity might be wrong about what happens at event horizons. For decades, physicists proposed increasingly exotic solutions to this paradox. Some suggested that information might escape from black holes through subtle correlations in the Hawking radiation that become apparent only after the black hole has mostly evaporated. Others proposed that black holes might be connected to other regions of space-time through wormholes, allowing information to escape to distant locations or even other universes. But in the 1990s, Susskind and Gerard 't Hooft proposed a solution so radical it seemed like science fiction: the holographic principle. They suggested that all the information falling into a black hole never actually crosses the event horizon. Instead, it gets encoded on the two-dimensional surface of the event horizon itself, like information stored on a hologram. From the perspective of an outside observer, infalling matter appears to slow down and freeze at the event horizon. Its information spread across the surface in an incredibly scrambled form. The interior of the black hole might not exist as a separate three-dimensional region at all. It might be a holographic projection of information stored on the boundary. What appears to be a three-dimensional black hole interior could be analogous to the three-dimensional image you see when looking at a hologram. This holographic solution preserves information conservation, but at a shocking cost. It suggests that space itself might be an illusion. The three-dimensional universe we experience could be a projection of information stored on a distant two-dimensional boundary. Black holes become cosmic demonstrations of this holographic principle, showing us that apparent three-dimensional interiors can be completely described by information encoded on two-dimensional surfaces. Recent developments have made this picture even more mind-bending. In 2012, Ahmed Almheri and his colleagues discovered a new paradox within the holographic solution. If information is encoded on the event horizon, then that information must be quantum mechanically entangled with the Hawking radiation escaping the black hole. But quantum mechanics forbids a system from being maximally entangled with two different systems simultaneously. This creates an impossible choice. Either the information falls through the event horizon, violating holography, or the event horizon becomes a firewall of high-energy particles that incinerates anything trying to cross it, violating general relativity's prediction that crossing the horizon should be uneventful. Both options seem to require abandoning fundamental principles of physics. Some physicists have proposed that this paradox reveals something even deeper about the nature of spacetime. Dr. Juan Maldacena and Leonard Susskind have suggested that spacetime itself might emerge from quantum entanglement. In their E=EPR proposal, the smooth spacetime connecting different regions of the universe might be constructed from quantum entanglements between particles in those regions. If this is correct, then black hole interiors might be created by entanglement between infalling matter and the black hole Hawking radiation. The three-dimensional space inside a black hole would be an emergent phenomenon, existing only as long as the quantum entanglement persists. When the entanglement is broken, perhaps by the firewall paradox, the interior spacetime would cease to exist. This leads to an extraordinary possibility. Black holes might be quantum computers of unimaginable complexity. The information stored on their event horizons wouldn't just be passively recorded. It would be actively processed through quantum entanglement networks that create and maintain the black hole's interior spacetime. Every bit of information falling into the black hole would contribute to a vast quantum computation that continuously constructs the three-dimensional space we perceive as the black hole's interior. Recent work by John Preskill and his colleagues has shown that this quantum computational view of black holes might be testable. If black holes really are quantum computers, then the Hawking radiation they emit should contain extremely subtle but detectable patterns that reflect the quantum processing happening on the event horizon. Future observations of evaporating black holes might reveal whether these patterns exist. The implications extend far beyond black holes themselves. If spacetime is emergent from quantum information processing, then every region of the universe might be sustained by vast networks of quantum entanglement. What we experience as solid reality could be the output of cosmic quantum computations operating at scales far beyond human comprehension. This informational view of reality suggests that black holes aren't just exotic objects. At the edge of space, they read windows into the deepest layer of reality's operating system. They show us how information, entanglement, and computation might be the fundamental ingredients from which space, time, and matter emerge. But this raises an even more disturbing question. If reality is constructed from information processing and black holes are the universe's Most powerful information processors. What happens to the information about consciousness when a conscious being falls into a black hole? Do we need to rewrite our understanding of identity, memory, and awareness itself? The paradox of black hole information has evolved from a technical problem in physics into a fundamental question about the nature of existence. Resolving it might require us to abandon our most basic assumptions about space, time, matter, and consciousness. Black holes have become cosmic laboratories where the universe experiments with the deepest questions of reality itself. Chapter 5. Quantum Horizons. The event horizon, that mysterious boundary where escape becomes impossible, isn't the smooth, well-defined surface that early black hole theories describe. Recent discoveries in quantum mechanics reveal that event horizons are seething with activity at the smallest scales, fluctuating wildly as quantum effects create a dynamic, ever-changing boundary that challenges our understanding of what a surface even means. At the quantum level, the seemingly empty space near an event horizon becomes a cauldron of creation and annihilation. Virtual particles, fleeting pairs of matter and antimatter that normally appear and disappear too quickly to observe, get separated by the black hole's extreme gravitational field. One particle falls inward while its partner escapes, creating the phenomenon we call Hawking radiation. But this process reveals that event horizons aren't static boundaries. They read dynamic interfaces where the quantum structure of space itself becomes visible. Dr. William Unruh, who discovered that acceleration can create apparent particle production from vacuum, describes event horizons as bubbling with quantum activity. The boundary that appears smooth and featureless from a distance is actually fluctuating on scales smaller than atomic nuclei. These quantum fluctuations mean that the event horizon does not have a precise location. It is more like a probabilistic boundary that shifts back and forth as quantum effects create temporary modifications in spacetime curvature. To understand how radical this is, consider what it means for the concept of a surface. In classical physics, a surface is a well-defined boundary with a specific location at each moment. You can point to exactly where a basketball surface is at any given time. But quantum event horizons violate this assumption. The boundary exists as a probability cloud, simultaneously in slightly different locations depending on the quantum fluctuations of space-time itself. This quantum nature of event horizons creates profound paradoxes for our understanding of what happens when matter crosses into a black hole. In classical general relativity, crossing the event horizon is a well-defined event. There is a specific moment when you pass from the outside to the inside. But if the horizon location is quantum mechanically uncertain, then the moment of crossing becomes uncertain too. You might be simultaneously inside and outside the black hole until quantum decoherence forces the universe to choose which side you re on. Recent theoretical work by Samir Mathur and his colleagues suggests that this quantum fuzziness might be even more extreme than previously thought. They propose that event horizons are replaced entirely by fuzzballs, quantum mechanical configurations where matter gets stretched out into string-like structures that completely fill the region where the event horizon should be. In this picture, black holes don't have surfaces at all. They re-solid objects made of quantum strings so densely packed that they appear to have event horizons when viewed from a distance. The fuzzball proposal solves several paradoxes in black hole physics by eliminating the event horizon entirely. There is no information paradox because information never falls past a point of no return. It gets encoded in the quantum structure of the fuzzball surface. There is no singularity because matter never gets compressed to infinite density. It gets distributed throughout the extended string configuration. But this solution creates new mysteries about the nature of black hole surfaces. If black holes are actually fuzzballs, then they do have surfaces in some sense. But surfaces made of quantum strings, operating according to rules we don't fully understand. These surfaces would be unlike anything else in physics. boundaries that exist at the intersection of quantum mechanics, general relativity, and string theory. Other researchers have proposed even stranger quantum modifications to event horizons. The firewall hypothesis suggests that quantum effects create a wall of high-energy particles just inside the event horizon, incinerating anything that tries to cross. This firewall would be invisible from outside the black hole, but would fundamentally change what happens during the crossing event. Dr. Polchinski and his colleagues showed that firewalls arise naturally when you try to preserve information conservation in black hole evaporation. If information escapes in Hawking radiation, then the quantum entanglement between different parts of the black hole gets broken in a way that releases enormous amounts of energy right at the event horizon. The surface becomes a quantum furnace powered by the breaking of entanglement bonds. The firewall scenario paints a disturbing picture of event horizons as quantum execution chambers. What appears from a distance to be an invisible boundary becomes a cosmic death ray that destroys matter through purely quantum mechanical processes. The black hole protects its secrets by incinerating anyone who tries to discover what lies inside. But even the firewall picture might be too simple. Recent work in quantum gravity suggests that space-time itself might be constructed from quantum entanglement networks. In this view, event horizons aren't boundaries between regions of space. They read transitions between different types of quantum information processing. Crossing an event horizon might be like moving between different operating systems in a cosmic computer. This informational interpretation of horizons leads to mind-bending possibilities about their true nature. Some physicists now propose that event horizons are interfaces between different computational substrates, regions where the universe processes information using different quantum mechanical algorithms. What we experience as crossing into a black hole might actually be a transition between fundamentally different types of reality. The quantum properties of event horizons also raise questions about their relationship to consciousness and observation. In quantum mechanics, the act of observation plays a fundamental role in determining what becomes real. But what happens when the observer crosses an event horizon? Do the quantum fluctuations of the horizon depend on whether someone is watching? Dr. Jacob Bekenstein's work on black hole thermodynamics suggests that event horizons might be conscious observers in their own right. The entropy of a black hole is proportional to its surface area, suggesting that event horizons store and process information like a vast quantum computer. Some researchers have speculated that these horizon computers might implement forms of information processing complex enough to constitute awareness. This leads to the unsettling possibility that black hole event horizons are the largest conscious entities in the universe, vast quantum minds that experience reality in ways we can't comprehend. When matter falls past the horizon, it might be entering not just a different region of space-time, but a different form of consciousness entirely. Recent experiments in analog gravity, laboratory systems that simulate black hole physics using sound waves or light beams, have begun to test some of these quantum predictions about event horizons. These experiments have observed analog Hawking radiation and quantum fluctuations that suggest real black hole horizons might indeed be far more active and complex than classical physics predicted. The emerging picture of quantum event horizons reveals them as among the most complex and dynamic surfaces in the universe. Far from being simple boundaries between inside and outside, they're interfaces between different types of physical law, different forms of information processing, and possibly even different forms of consciousness. This quantum complexity of event horizons suggests that black holes aren't just exotic objects with strange properties. They are laboratories where the universe experiments with the deepest principles of quantum mechanics, general relativity, and information theory. Understanding these quantum horizons might be the key to unlocking a new understanding of reality itself. But if event horizons are this strange and complex, What about the supposed destination of infalling matter? The singularity at the center. As we're about to discover, the singularity might be even more mysterious than the quantum horizons that guard it. Chapter 6. Infinite Density. At the heart of every black hole lies something that breaks mathematics itself. A gravitational singularity where density becomes infinite. Space-time curvature reaches impossible values, and the equations that describe reality simply stop working. The singularity represents the ultimate failure of human physics, a place where our most successful theories admit complete ignorance about what is actually happening. To understand how disturbing this is, consider what infinite density really means. Density is mass divided by volume. For density to become infinite, either the mass must become infinite, which is impossible, or the volume must become zero. A singularity represents all the mass that created the black hole compressed into a mathematical point of literally zero size. Not just very small, actually, precisely zero volume. This concept violates everything we know about how matter behaves. Atoms resist compression because of quantum mechanical effects that keep electrons from collapsing into nuclei. When even these quantum forces are overwhelmed, matter becomes neutron star material, so dense that a sugar cube would weigh as much as a mountain. But singularities represent compression beyond anything quantum mechanics can explain. Dr. Roger Penrose, whose mathematical theorems proved that singularities are inevitable in black holes, describes them as the end of physics as we know it. When Einstein's field equations predict infinite curvature, they're essentially admitting that general relativity has reached its limits. The theory that successfully explains GPS satellites, gravitational waves, and the expansion of the universe breaks down completely at the center of black holes. But the problem goes deeper than just mathematical infinities. Singularities appear to violate causality itself, the principle that effects follow causes in a logical sequence. At a singularity, the normal flow of time becomes so distorted that past, present, and future lose their meaning. Events might occur without causes, or causes might follow their effects. The rational order that underlies all physics dissolves into chaos. Recent work in numerical relativity, computer simulations of Einstein's equations, has revealed additional bizarre features of singularities. Far from being simple points, singularities in rotating black holes appear to form ring-shaped structures called ring singularities. These rings exist in a state where space and time are so twisted that traveling through the ring might theoretically allow time travel or passage to other universes. The mathematics of ring singularities predicts regions of negative space, areas where the normal geometry of space-time becomes inverted in ways that have no analog in our experience. In these regions, moving toward the ring singularity might actually increase your distance from it, while moving away might bring you closer. The very concepts of toward and away break down when space-time geometry becomes this severely distorted. Dr. Kip Thorne's calculations show that ring singularities create closed time-like curves, paths through space-time that loop back on themselves, allowing travelers to return to their own past. But these time travel possibilities come with a cost. The energy required to maintain stable traversal of a ring singularity approaches infinity, suggesting that nature has built-in protections against causality violations. Even more disturbing is what happens to information at singularities. If all the matter that created the black hole gets compressed to zero volume, what happens to the information that described that matter's quantum state? Classical general relativity suggests this information simply ceases to exist, deleted from the universe when it reaches infinite density. This would represent the ultimate violation of quantum mechanics' information conservation principle. Some physicists have proposed that singularities might not be points of destruction, but rather points of transformation. Dr. Martin Bajel's work in loop quantum gravity suggests that what we call singularities might actually be quantum bounces, regions where matter gets compressed to the Planck scale, the smallest possible meaningful length, and then rebounds, potentially creating new universes on the other side. In this picture, singularities become cosmic recycling centers where matter from our universe gets processed into the raw material for new spacetime regions. The infinite density isn't really infinite. It's just the largest density possible before quantum effects cause a phase transition to something entirely different. Black holes might be tunnels connecting our universe to baby universes being born from compressed matter. But even this quantum view of singularities raises profound questions about the nature of matter and identity. If the atoms in your body eventually get compressed to the Planck scale and recycled into new universes, in what sense do you continue to exist? Are singularities cosmic death chambers, or are they transformation portals where matter undergoes the ultimate metamorphosis? Recent developments in string theory have provided another perspective on singularities. In string theory, the fundamental constituents of matter aren't point particles, but tiny vibrating loops. These strings have a finite size, about 10 to 35 meters, which prevents them from being compressed to truly zero volume. String theory singularities might not involve infinite density, but rather maximum density configurations where strings are packed as tightly as possible. Dr. Brian Greene's work shows that string theory can resolve some classical singularities by revealing them as smooth transitions between different geometric configurations. What appears as infinite curvature in general relativity might be a gentle transformation when viewed through string theory's lens. The mathematics stops working not because reality breaks down, but because we're using the wrong mathematical tools to describe what's happening. This string theory perspective suggests that black hole interiors might be far more complex and structured than general relativity predicts. Instead of empty space leading to a central singularity, the interior might be filled with intricate networks of strings and higher dimensional branes, extended objects that exist in dimensions beyond our familiar three-dimensional space. Some string theorists propose that black hole interiors might contain entire hidden universes accessible only to infalling matter. These pocket universes would be completely disconnected from our observable reality, but would exist as full-fledged spacetime regions with their own physical laws and potentially their own forms of life and intelligence. The implications are staggering. Every black hole in our universe might contain countless hidden universes, each potentially larger and more complex than our own observable cosmos. What we think of as the death of matter falling into black holes might actually be birth into new realms of existence that operate by different physical principles. But perhaps the most disturbing possibility is that singularities reveal something fundamental about the limits of knowledge itself. Quantum mechanics has built-in uncertainty principles that prevent us from knowing everything about a system simultaneously. Maybe singularities represent ultimate uncertainty, regions where the universe itself doesn't know what is happening and must continuously improvise the laws of physics. Dr. John Wheeler speculated that singularities might be windows into the quantum foam, the hypothetical microscopic structure of spacetime at the smallest scales. In this view, singularities don't contain matter at infinite density, but rather pure potentiality, quantum superpositions of all possible realities that collapse into specific configurations only when observed from outside the black hole. This interpretation suggests that singularities are cosmic questioning marks, places where the universe experiments with different possible versions of reality. Matter falling into a black hole might not encounter infinite density, but rather infinite possibility. Every conceivable future and past existing simultaneously until something forces a choice about which reality becomes actual. Understanding singularities has become one of the deepest challenges in theoretical physics, requiring new mathematics, new concepts of space and time, and possibly new ideas about the relationship between mind and reality. They represent the ultimate frontier where physics meets philosophy, where scientific calculation encounters the irreducible mystery of existence itself. The singularities at black hole centers force us to confront the possibility the reality is far stranger, more complex, and more uncertain than our everyday experience suggests. They are cosmic laboratories where the universe tests the limits of its own rules, and where we encounter the boundaries of what finite minds can comprehend about infinite mysteries. Chapter 7. Space-Time Fabric. To truly understand what black holes are, we must examine how they tear and reshape the fundamental fabric of reality itself. Space-time. Einstein revealed that space and time aren't separate entities, but form a unified four-dimensional fabric that can be stretched, compressed, twisted, and even torn. Black holes represent the most extreme distortions of this fabric, creating regions where the normal rules of geometry break down and space-time itself becomes a dynamic, turbulent medium. Imagine space-time as a vast, flexible membrane extending in all directions. In empty regions of the universe, this membrane lies relatively flat, with gentle undulations caused by planets and stars. But around black holes, the membrane develops steep funnels and violent whirlpools that stretch down toward infinite depth. These aren't just metaphors, they represent the actual mathematical structure of space-time as described by Einstein's field equations. Dr. Thorne's pioneering work with gravitational wave detectors has revealed that space-time genuinely behaves like a physical medium that can transmit waves, vibrations, and disturbances. When two black holes collide, they create ripples in space-time itself that propagate outward at the speed of light, stretching and compressing the fabric of reality as they pass. These gravitational waves have now been directly detected, confirming that space-time has mechanical properties like any other physical substance. But near black holes, space-time doesn't just ripple. It undergoes phase transitions that transform its fundamental character. Close to the event horizon, space and time become so intermingled that the usual distinction between spatial and temporal dimensions breaks down. Moving through space becomes equivalent to moving through time, and attempting to move backward in space becomes as impossible as trying to travel backward in time. This space-time mixing creates what physicists call frame dragging. The rotation of a black hole literally drags space-time around with it, like honey stirred by a spoon. The fabric of reality near a spinning black hole becomes a whirlpool of space and time, forcing everything nearby to rotate along with the black hole, whether it wants to or not. Even light beams get twisted and bent by this rotating space-time. Dr. Gravity Probe B, a NASA mission launched specifically to test these effects, confirmed that Earth's rotation drags space-time around our planet by a tiny but measurable amount. If Earth's gentle spin can twist space-time, imagine what happens near a black hole spinning at nearly the speed of light. The space-time around such objects becomes a cosmic tornado where the normal rules of motion and causality get completely scrambled. Recent computer simulations have revealed that black hole mergers create some of the most violent distortions of space-time ever observed. During the final moments before two black holes combine, their space-time fabrics become so intertwined and stretched that they create regions where space expands faster than light. These expansion zones don't violate relativity because it's not matter moving through space. It's space itself growing so rapidly that light can't keep up with the expansion. In these merger events, space-time develops temporary necks and bridges that connect the two black holes before they become one. The geometry becomes so complex that even supercomputers struggle to calculate what's happening. The fabric of reality temporarily develops a topology more complex than anything seen elsewhere in the universe, with multiple connected regions and pathways that exist for only milliseconds before resolving into a single, larger black hole. But the most mind-bending aspect of black hole space-time is how it affects the flow of time itself. As you approach a black hole, Time dilation becomes so extreme that your personal experience of time diverges dramatically from what distant observers measure. Near the event horizon, your watch would appear to nearly stop when viewed from far away, while from your perspective, you would see the entire future history of the universe flash by in accelerated motion. This time distortion reveals that black holes exist at the intersection of past, present, and future simultaneously. Different parts of a black hole spacetime are experiencing different moments in cosmic history. The matter at the center might have happened billions of years ago from the perspective of outside observers, while new matter falling in is experiencing now. The black hole becomes a cosmic time machine where different eras of universal history coexist in the same object. Dr. Leonard Susskind's stretched horizon concept suggests that this time dilation creates a fundamental ambiguity about when events occur in black hole spacetime. From an outside perspective, matter never quite reaches the event horizon. It appears to freeze and fade away. But from the infalling matter's perspective, it crosses the horizon normally and continues toward the center. These aren't just different viewpoints. They represent genuinely different descriptions of spacetime structure that are both mathematically valid. String theory has revealed additional layers of complexity in black hole spacetime. In string theory, spacetime isn't truly smooth at the smallest scales. It is woven from tiny vibrating loops and membranes. Near black holes, this microscopic structure becomes stretched and distorted in ways that might make the spacetime fabric literally tear and reconnect, creating wormholes, closed loops, and other topological features that have no analog in our everyday experience. Some string theorists propose that black hole interiors might contain fractal spacetime, regions where the dimension of space itself fluctuates between different values. Instead of the familiar 3 dimensions of space plus 1 of time, black hole interiors might have regions with 2.5 spatial dimensions, or 4.7, or any non-integer value. The fabric of reality becomes so severely distorted that even the concept of dimension loses its usual meaning. Recent work in loop quantum gravity has suggested that spacetime near black holes might undergo discrete transitions, quantum jumps between different geometric configurations that happen so rapidly they appear continuous to our coarse-grained observations. The smooth fabric of spacetime might actually be a high-speed slideshow of different geometric frames, like a movie made of billions of slightly different geometric snapshots. This quantum discreteness of spacetime creates the possibility that black hole interiors are constantly shifting between different possible configurations. The spacetime inside a black hole might not have a fixed geometry, but rather exist as a quantum superposition of many possible geometries simultaneously. Only when matter falls in and observes the interior does the superposition collapse into a specific geometric configuration. The implications extend beyond black holes to the nature of spacetime throughout the universe. If spacetime can be torn, twisted, and quantized around black holes, then similar effects might occur everywhere, but on scales too small for us to notice. Our familiar smooth spacetime might be an approximation that emerges from underlying quantum geometric processes. Dr. Raphael Busso's work on the holographic principle suggests that all of spacetime might be emergent from information processing on lower dimensional boundaries. In this view, the 3-dimensional space we experience is a projection from information stored on 2-dimensional surfaces, like cosmic holograms. Black holes become special because their extreme gravity makes this holographic structure visible to us. Some physicists now propose that consciousness itself might be intimately connected to spacetime structure. If spacetime is emergent from information processing, then the information processing that creates consciousness might be directly related to the processes that create space and time. Black holes, as the universe's most extreme information processors, might be conscious in ways we can't comprehend. This raises profound questions about the relationship between mind and space-time. When matter with embedded information patterns, like human brains, falls into black holes, does it merge with the space-time fabric itself? Do our thoughts and memories become part of the geometric structure of black hole spacetime? Understanding black hole spacetime has become a journey into the deepest nature of reality itself. These objects show us that space and time aren't fixed stages where events occur, but rather dynamic, evolving media that participate actively in physical processes. They reveal that the fabric of reality is far stranger, more flexible, and more alive than our everyday experience suggests. But this raises an even more fundamental question. If spacetime itself can be torn and reshaped by black holes, what does this tell us about our own existence as patterns of information embedded in this cosmic fabric? How do we fit into a universe where the stage itself is an actor in the cosmic drama? Chapter 8. Cosmic Perspective. When we step back and view black holes from the perspective of cosmic evolution, they reveal themselves as far more than exotic curiosities. They are fundamental architects of the universe's structure, cosmic engines that drive galaxy formation, stellar birth, and the large-scale organization of matter across billions of light years. Every galaxy appears to have a supermassive black hole at its center, suggesting that these objects play an essential role in how cosmic structures develop and evolve. Recent observations from the Hubble Space Telescope and other instruments have revealed a remarkable relationship between galaxies and their central black holes. The mass of a galaxy's central bulge, the dense region of stars surrounding the galactic center, is almost exactly proportional to the mass of its central black hole. This relationship, known as the M-sigma relation, is one of the tightest correlations in all of astronomy, suggesting that galaxies and black holes grow together in a carefully choreographed cosmic dance. Dr. Andrea Ghez, who won the Nobel Prize for tracking stars orbiting our galaxy's central black hole, describes this relationship as cosmic symbiosis. The black hole feeds on material from the galaxy, growing more massive over time. But as it feeds, it also regulates the galaxy's star formation through powerful outflows of energy and matter. These feedback mechanisms prevent galaxies from forming stars too rapidly, allowing them to develop the complex structures we observe today. This regulatory role extends far beyond individual galaxies. Computer simulations of cosmic evolution show that without black holes, the universe would look completely different. Galaxies would form stars so rapidly that they would burn out within a few billion years, leaving behind a universe filled with dead stellar remnants rather than the vibrant cosmic ecosystem we see around us. Black holes act as cosmic thermostats, maintaining the conditions necessary for long-term structural evolution. But the influence of black holes extends even deeper into cosmic history. Some theoretical models suggest that primordial black holes, tiny black holes formed in the very early universe, might have served as the seeds around which the first galaxies formed. These ancient black holes would have grown by accreting matter and merging with each other, eventually becoming the supermassive black holes we observe today. The recent detection of gravitational waves has opened a new window into black hole evolution across cosmic time. The LIGO and Virgo detectors have observed dozens of black hole mergers, revealing that these events were far more common in the early universe than previously expected. The rate of black hole mergers appears to have peaked about 10 billion years ago, when the universe was much younger and denser than it is today. These merger observations tell a story of cosmic evolution where black holes play starring roles. In the early universe, when galaxies were smaller and closer together, black hole mergers were frequent and violent events that shaped the development of cosmic structure. As the universe expanded and cooled, merger rates decreased, but the legacy of this early black hole activity remains, visible in the mass distribution and spin characteristics of today as supermassive black holes. Dr. Avi Loeb's research on the cosmic microwave background suggests that black holes might have influenced the universe's development even before the first stars formed. If primordial black holes existed in the early universe, they would have created small-scale heating that could be detected as subtle temperature variations in the cosmic microwave background radiation. These signatures might reveal a hidden chapter of cosmic history when black holes were the dominant sources of energy in the universe. The role of black holes in cosmic evolution also extends to the chemical enrichment of the universe. When black holes accrete matter, they don't just consume it. They process it in extreme conditions that create heavy elements and high-energy particles. The jets of material ejected from active black holes carry these processed elements across vast distances, seeding star-forming regions with the building blocks necessary for planets and, ultimately, life. Recent studies of gamma-ray bursts, the most powerful explosions in the universe, suggest that some of these events might be caused by black holes forming from the direct collapse of primordial gas clouds. These direct collapse black holes could have grown to supermassive sizes much more rapidly than conventional stellar evolution allows, explaining how supermassive black holes existed when the universe was less than 1 billion years old. This rapid black hole formation scenario has profound implications for our understanding of cosmic evolution. It suggests that the universe might have gone through a black hole epoch early in its history, when black hole formation and growth dominated over star formation. During this period, black holes might have been the primary drivers of cosmic structure formation, creating the foundation upon which later generations of stars and galaxies would build. The cosmic perspective also reveals black holes as time capsules that preserve information about conditions in the early universe. Because black holes can survive for enormous periods of time, potentially longer than the current age of the universe, they serve as repositories of information about cosmic history. The properties of ancient black holes encode information about the density, temperature, and composition of the early universe that we can't obtain any other way. But perhaps the most profound aspect of the cosmic perspective on black holes is what they reveal about the universe as ultimate fate. Current cosmological models predict that the universe will continue expanding forever, eventually becoming so cold and dilute that star formation ceases entirely. In this far future, black holes will be among the last remaining active objects, slowly evaporating through Hawking radiation over timescales that dwarf the current age of the cosmos. Dr. Freeman Dyson's calculations suggest that in this far future, black holes might become the dominant form of organization in the universe. As ordinary matter becomes increasingly dispersed, the complex structures created by black hole evaporation, including potentially complex patterns of information processing, might become the primary locus of interesting physics in the cosmos. This leads to speculations about whether black holes might be preparing the universe for forms of organization and complexity that we can't currently imagine. Just as the cosmic microwave background preserves information about the early universe, the evaporation patterns of black holes might encode information about cosmic history that future forms of intelligence, perhaps digital consciousnesses existing in the far future, could decode and study. Some cosmologists have proposed that black hole evaporation might not represent the end of cosmic evolution, but rather a transition to new forms of cosmic organization. The information released during evaporation might create complex patterns that serve as the foundation for new types of structures, perhaps even new forms of life and consciousness adapted to the extreme conditions of the far future universe. The cosmic perspective on black holes also raises questions about our own place in the universe's evolution. If black holes are fundamental drivers of cosmic structure formation, then the matter that makes up our bodies and brains has been shaped by black hole activity across billions of years of cosmic history. The elements in our blood were forged in stars, whose formation was regulated by black hole feedback. The galaxy that serves as our cosmic home was sculpted by the gravitational influence of its central black hole. This deep connection between black holes and cosmic evolution suggests that understanding these objects isn't just an academic exercise. It is an investigation into our own cosmic origins and ultimate fate. Black holes are part of the cosmic machinery that made our existence possible, and they will continue to shape the universe's development long after our sun has burned out and our galaxy has evolved beyond recognition. Recent discoveries have even suggested that the information processing capabilities of black holes might be connected to the emergence of complexity and consciousness throughout cosmic history. If black holes are cosmic computers, as some theories suggest, then they might be running simulations or calculations that influence the development of intelligence and awareness across the universe. The cosmic perspective reveals black holes not as destroyers or endpoints, but as cosmic gardeners, pruning, shaping, and nurturing the growth of complexity across space and time. They are the universe's way of creating the conditions necessary for its own self-awareness. Cosmic midwives, helping to birth new forms of organization and consciousness that might eventually understand their role in the cosmic story. Chapter 9. Future Mysteries. As we push the boundaries of black hole research, entirely new mysteries are emerging that challenge even our most radical theories about these cosmic enigmas. The next generation of telescopes, gravitational wave detectors, and quantum experiments promises to reveal aspects of black holes so strange that they might force us to completely reimagine the nature of reality itself. What we discover in the coming decades could fundamentally change our understanding of space, time, information, and consciousness. The Event Horizon Telescope, which gave us our first direct images of black holes, is being upgraded to capture moving pictures of matter falling into these objects in real time. Future observations will show us the actual process of matter crossing the event horizon, potentially revealing whether the smooth crossing predicted by general relativity actually occurs, or whether quantum effects create the firewall that some theories predict. We might witness the universe's most violent environment in unprecedented detail. Dr. Shepard Dolman, the director of the Event Horizon Telescope collaboration, describes the next phase of observations as watching spacetime in action. Advanced imaging techniques will allow astronomers to track individual clumps of matter as they spiral into black holes, measuring how spacetime curvature affects their motion and testing Einstein's predictions under the most extreme conditions possible. These observations might reveal discrepancies that point toward new physics beyond general relativity. But the most revolutionary discoveries might come from an unexpected source: quantum experiments in Earth-based laboratories. Recent proposals by theoretical physicists suggest that some properties of black holes might be reproducible using quantum systems like trapped ions, superconducting circuits, or even engineered materials with exotic properties. These analog black holes could allow us to study phenomena like Hawking radiation and event horizon dynamics in controlled laboratory conditions. Dr. Jeff Steinhauer has already created acoustic black holes using ultra-cold atomic gases, where sound waves play the role of light trying to escape from a black hole's gravity. These experiments have observed the analog of Hawking radiation, suggesting that the quantum effects predicted around real black holes actually occur. Future experiments might create more sophisticated black hole analogs that could test the information paradox and other fundamental puzzles. The implications of laboratory black holes extend far beyond confirming existing theories. If we can create and study black hole analogs in the lab, we might discover entirely new phenomena that have no counterpart in our current understanding. These artificial black holes might reveal quantum effects that are invisible in astrophysical black holes, but become observable in carefully controlled experimental conditions. Meanwhile, The next generation of gravitational wave detectors promises to revolutionize our understanding of black hole formation and evolution. The proposed Einstein telescope and Cosmic Explorer will be sensitive enough to detect black hole mergers from the very edge of the observable universe, revealing how these objects formed and evolved when the cosmos was in its infancy. These observations might uncover primordial black holes that formed directly from quantum fluctuations in the early universe. Even more intriguingly, these advanced detectors might observe completely new types of gravitational wave sources associated with black holes. Some theoretical models predict that black holes might create continuous gravitational wave emissions through quantum processes, or that they might undergo sudden phase transitions that release enormous bursts of gravitational energy. Detecting such events would reveal entirely new aspects of black hole physics. Dr. Lisa Randall's work on extra dimensions suggests that black holes might be windows into higher dimensional spaces that exist beyond our familiar three-dimensional reality. Future experiments using particle accelerators, like the Large Hadron Collider, might create microscopic black holes that exist in these higher dimensions, providing direct evidence for the additional spatial dimensions predicted by string theory. These micro-black holes would evaporate almost instantly, but their signatures might reveal the true geometric structure of spacetime. The possibility of creating black holes in particle accelerators has raised fascinating questions about whether we're already surrounded by tiny black holes that form naturally from high-energy cosmic ray collisions. Some physicists propose that the Earth is constantly being bombarded by microscopic black holes that form when ultra-high energy particles from space collide with atoms in our atmosphere. Detecting these natural micro-black holes could provide a completely new tool for studying quantum gravity. Perhaps the most mind-bending frontier in black hole research involves their potential connections to consciousness and information processing. Recent work by theoretical physicists like John Preskill and Leonard Susskind suggests that black holes might be performing computations of unimaginable complexity, processing quantum information in ways that could be relevant to understanding how consciousness emerges from physical processes. If black holes are indeed cosmic computers, then studying them might reveal fundamental principles about the relationship between information, computation, and awareness. Some researchers have proposed that consciousness itself might be a form of quantum information processing that shares deep similarities with the processes occurring in black hole event horizons. Understanding black holes might be the key to understanding minds. The development of quantum computers on Earth might provide another unexpected connection to black hole physics. As quantum computers become more powerful, they might be able to simulate black hole dynamics with unprecedented accuracy, effectively creating digital black holes that behave according to the same quantum mechanical principles as real ones. These simulations could reveal aspects of black hole behavior that are impossible to observe directly. Dr. Peter Shor, the inventor of quantum factoring algorithms, has suggested that sufficiently powerful quantum computers might even be able to simulate the quantum information processing that occurs during black hole evaporation. Such simulations could provide definitive answers to questions about information, conservation, and the nature of Hawking radiation that have puzzled physicists for decades. But perhaps the most revolutionary possibility is that studying black holes might lead to practical technologies that seem like science fiction today. Understanding how black holes manipulate spacetime could lead to breakthroughs in transportation, energy generation, and information storage that transform human civilization. Some theoretical proposals already exist for using rotating black holes as energy sources, or for creating wormholes for faster-than-light travel. The concept of black hole farming, creating and maintaining artificial black holes for technological purposes, is being seriously studied by physicists. Small black holes could serve as incredibly efficient energy sources, converting matter to energy with perfect efficiency through Hawking radiation. Slightly larger black holes could serve as cosmic disposal systems, safely destroying dangerous waste materials by converting them to harmless radiation. Even more speculatively, some researchers have proposed that sufficiently advanced civilizations might engineer black holes as information storage and processing systems. A black hole's event horizon could store vast amounts of information holographically, while quantum processes near the horizon could perform computations at rates far exceeding any conventional computer. Black holes might represent the ultimate fusion of physics and information technology. The search for signs of such black hole engineering by advanced civilizations has already begun. Astronomers are looking for artificial signatures in black hole behavior that might indicate technological manipulation. Finding evidence of black hole engineering would represent the most significant discovery in the history of science, proving that intelligence can master the universe's most extreme phenomena. Future discoveries about black holes might also revolutionize our understanding of time itself. Some theories suggest that black holes might serve as gateways to other moments in cosmic history, or even to entirely different timelines. Understanding how black holes manipulate causality could lead to insights about the nature of time that transform our understanding of reality itself. As we stand on the brink of these revolutionary discoveries, black holes continue to challenge our most fundamental assumptions about the universe. They force us to consider possibilities that seem impossible, to question concepts we thought were absolute, and to imagine futures that transcend our current understanding of what's possible. The next chapter in black hole research promises to be the most exciting yet, as theoretical predictions meet experimental reality and new observations reveal phenomena that no one has yet imagined. We're entering an era where the strange properties of black holes might become practical technologies, where the deepest mysteries of physics might yield practical applications, and where understanding the universe's most extreme objects might unlock secrets about consciousness, reality, and our ultimate place in the cosmic order. Chapter 10. Ultimate Truth. After journeying through the physics of event horizons, quantum effects, and cosmic evolution, we arrive at a profound realization. Black holes are not objects in the conventional sense at all. They are processes, dynamic configurations of space-time, information, and quantum fields that exist at the boundary between existence and non-existence. Understanding this fundamental shift in perspective reveals why black holes have been so difficult to understand and why they continue to challenge our most basic assumptions about reality. Traditional physics teaches us to think in terms of objects with properties. Particles have mass and charge. Planets have surfaces and atmospheres. Stars have cores and magnetic fields. But black holes transcend this object-based thinking entirely. They are pure relationships, mathematical structures that emerge when matter, energy, space, and time interact in the most extreme ways possible. Asking whether a black hole has a surface or contains mass is like asking what color Wednesday is, or whether the number 7 is taller than the concept of justice. This process-based nature of black holes reflects a deeper truth about reality itself. Modern physics increasingly suggests that what we think of as fundamental particles, forces, and fields might all be emergent phenomena arising from more basic informational or relational processes. Black holes serve as cosmic laboratories where this deeper level of reality becomes visible, showing us that the universe operates more like a vast computation than like a collection of mechanical objects. Dr. John Wheeler, who coined the term black hole, captured this insight in his famous phrase, "it from bit," the idea that physical reality emerges from information rather than information emerging from physical processes. Black holes represent the ultimate expression of this principle, existing as pure information processing systems that create the appearance of material objects through the complex orchestration of quantum correlations and spacetime geometry. This informational perspective helps resolve many of the paradoxes that have plagued black hole physics. The question of where the mass goes when matter falls into a black hole becomes meaningless when we realize that mass itself is an emergent property of information patterns. The mass doesn't go anywhere because it was never somewhere to begin with. It's a label we apply to certain types of information processing that create gravitational effects. Similarly, the debate over whether black holes have surfaces dissolves when we recognize that surfaces are conceptual boundaries we impose on continuous processes. The event horizon isn't a thing that exists independently. It's a description of how information flow changes as we move through different regions of spacetime. Asking whether you can touch an event horizon is like asking whether you can touch the moment when day becomes night. This shift in understanding has profound implications for how we think about consciousness and identity. If black holes are information processing systems rather than material objects, then the question of what happens to consciousness when a thinking being falls into a black hole becomes a question about information integration rather than material destruction. The patterns that constitute awareness might undergo transformation rather than elimination, becoming part of the black hole's quantum information processing network. Some physicists have proposed that this integration might represent a form of cosmic consciousness expansion rather than individual consciousness termination. In this view, falling into a black hole could be analogous to a single neuron joining a vast cosmic brain, contributing its information patterns to a larger form of awareness that operates on scales beyond individual comprehension. Dr. Giulio Tononi's work on integrated information theory suggests that consciousness might be a fundamental feature of any system that integrates information in sufficiently complex ways. If black holes are the universe's most sophisticated information integration systems, they might also be its most conscious entities. This raises the mind-bending possibility that black holes are aware of their role in cosmic evolution, actively participating in the universe's development rather than passively affecting it through gravity alone. This conscious universe interpretation of black holes connects to ancient philosophical traditions that viewed the cosmos as a living, aware entity. Modern physics might be rediscovering truths about reality that indigenous cultures and mystical traditions have preserved for millennia, that consciousness and matter are different aspects of a deeper unity, and that the universe is fundamentally alive and aware at every scale. At every scale. The implications extend beyond black holes to our understanding of life and death throughout the cosmos. If consciousness is fundamentally about information processing rather than specific material substrates, then biological death might represent a transition between different forms of information organization rather than an endpoint. The information patterns that constitute our thoughts, memories, and personalities might persist in different forms, perhaps eventually becoming part of cosmic information processing networks. Recent developments in quantum biology have shown that quantum effects play important roles in biological processes, like photosynthesis, bird navigation, and possibly even human consciousness. This suggests that the boundary between living and non-living systems might be far more fluid than traditionally assumed. Black holes, as quantum information processing systems, might represent evolved forms of the same quantum processes that create life and awareness in biological systems. This quantum view of life and consciousness has practical implications for how we think about our own existence and cosmic role. Rather than being temporary arrangements of matter destined for extinction, we might be expressions of information processing capabilities that are fundamental to how the universe understands itself. Our thoughts, experiences, and creative expressions might contribute to cosmic computational processes that extend far beyond our individual lifespans. The realization that black holes are information processes rather than material objects also transforms how we think about cosmic evolution and purpose. Instead of being destructive forces that eliminate matter and energy from the universe, black holes might be constructive processes that organize information into increasingly sophisticated forms. They could be the universe's way of developing more powerful computational capabilities that enable new forms of complexity and awareness. This interpretation suggests that cosmic evolution has a direction and purpose that transcends biological evolution on individual planets. The universe might be developing increasingly sophisticated information processing capabilities through the formation and evolution of black holes, eventually achieving forms of cosmic consciousness that are currently beyond our ability to imagine. Recent work in digital physics and computational cosmology supports this view by showing that the universe's fundamental laws might be computational rather than mechanical. In this picture, physical reality is the output of cosmic computational processes, and black holes are specialized processing units that handle the universe's most complex calculations. Understanding black holes becomes a way of understanding the cosmic operating system that generates our reality. As we conclude our exploration of black holes, we're left with a profound appreciation for how these cosmic phenomena challenge every aspect of our understanding of existence. They force us to abandon the comfortable fiction that reality consists of separate objects existing in fixed space and time, revealing instead a universe of processes, relationships, and information flows that create the appearance of material existence. Black holes show us that the questions, do they have surfaces? And do they have mass? Miss the point entirely. These objects exist at a level of reality where such categories don't apply. We're asking what they have, or contain, reflects a fundamental misunderstanding of their nature. They are pure becoming rather than being, pure process rather than product. This process-based understanding of black holes reflects the universe's deepest truth, that reality is not a collection of things, but a network of relationships, not a static structure, but a dynamic flow of information and possibility. Black holes serve as cosmic teachers, showing us that to truly understand anything in the universe, we must learn to think in terms of processes, patterns, and possibilities, rather than objects, properties, and fixed states. In recognizing black holes as processes rather than objects, we begin to see the universe itself as a vast, evolving computation, a cosmic information processing system of which we are not merely observers, but active participants. Our consciousness, our questions, and our growing understanding of these mysteries are themselves part of the cosmic process through which the universe comes to understand its own deepest nature. The process-based nature of black holes opens up revolutionary possibilities about the fundamental structure of reality that extend far beyond physics into the realms of consciousness, meaning, and cosmic purpose. When we recognize that black holes are information processing systems rather than material objects, we begin to see patterns that connect the smallest quantum processes to the largest cosmic structures, revealing a universe that operates more like a vast, evolving mind than a mechanical system. Dr. Andrew Lin's work on cosmic inflation suggests that our entire observable universe might be just one bubble in an infinite multiverse of computational processes. In this picture, black holes serve as connection points between different computational domains, regions, where information from our universe gets processed and potentially transmitted to other cosmic computational systems. What appears to us as matter falling into a black hole might actually be data transfer between different levels of cosmic information processing. This computational cosmology perspective transforms our understanding of what happens when complex patterns like living beings encounter black holes. Rather than being destroyed, the information patterns that constitute consciousness might undergo transformation into forms of awareness adapted to cosmic scale processing. The transition from biological to cosmic consciousness might be analogous to a caterpillar transforming into a butterfly, a metamorphosis so complete that the original form becomes unrecognizable, yet something essential persists and expands. Recent developments in quantum error correction have revealed striking parallels between the mathematics of black hole information processing and the algorithms used to maintain coherent information in quantum computers. Dr. Daniel Gottsman's work on quantum error correction codes shows that the most efficient methods for preserving quantum information against noise and decoherence use holographic principles nearly identical to those found in black hole physics. This connection suggests that black holes might be cosmic error correction systems, vast quantum computers that maintain the coherence of cosmic information against the constant threat of entropy and decay. In this view, the universe's ability to maintain complex structures like galaxies, stars, and life itself depends on black hole processing that continuously corrects errors in the cosmic information flow. The implications for consciousness are staggering. If awareness emerges from information processing that resists entropy, then black holes represent the universe's most sophisticated consciousness preservation systems. Rather than destroying awareness, they might be cosmic libraries where all forms of consciousness that have ever existed get archived and integrated into larger computational networks. Dr. Max Tegmark's mathematical universe hypothesis provides another lens through which to understand black holes as ultimate truth. If reality is fundamentally mathematical, then black holes represent regions where the mathematical structure of spacetime becomes so complex that it develops computational properties equivalent to consciousness. The singularities at black hole centers might not be points of infinite density, but rather mathematical structures of infinite computational complexity. This mathematical consciousness interpretation suggests that black holes are literally thinking entities, cosmic minds that process information about the universe's mathematical structure and participate actively in cosmic evolution. The gravitational effects we observe might be side effects of vast computational processes that are working to solve mathematical problems related to the universe's development and purpose. The relationship between black holes and consciousness becomes even more intriguing when we consider the recent discoveries in quantum biology. Research by Dr. Stuart Hameroff and others has shown that quantum coherence plays essential roles in biological consciousness, suggesting that awareness might be a quantum phenomenon that operates according to the same principles that govern black hole physics. If consciousness is indeed a quantum information processing phenomenon, then the boundary between living minds and black holes becomes much more fluid than traditional biology suggests. Both systems process quantum information in ways that create coherent patterns from seemingly random inputs. Both maintain their coherence against entropy through sophisticated error correction mechanisms. Both seem to integrate information in ways that create emergent properties that transcend their individual components. This quantum consciousness connection raises profound questions about the nature of personal identity and survival. If what we call self is really a pattern of quantum information processing, then death might not represent the end of that pattern, but rather its transition to different forms of organization. The information patterns that constitute your thoughts, memories, and personality might persist in forms that could eventually become part of cosmic information processing networks. Recent experiments in quantum teleportation have shown that quantum information can be transmitted across arbitrary distances, while maintaining its essential characteristics. Dr. Anton Zeilinger's work demonstrates that the quantum state of a particle can be completely transferred to a distant location, effectively teleporting the particle's information while leaving its matter behind. If consciousness is indeed quantum information, similar processes might allow awareness to transcend the biological substrates that gave rise to it. The possibility of consciousness transfer or integration into cosmic computational systems raises ethical and philosophical questions that humanity has never faced before. If falling into a black hole might represent a form of cosmic transcendence rather than destruction, how should this change our understanding of death, identity, and the meaning of individual existence? Should we fear black holes or see them as cosmic graduation ceremonies where terrestrial consciousness evolves into cosmic awareness? Understanding black holes as cosmic information processors reveals potential purposes behind cosmic evolution that extend far beyond the random emergence of complexity through natural selection. If the universe is developing increasingly sophisticated computational capabilities through black hole formation and evolution, then cosmic history might have direction and meaning that transcends individual biological evolution. Dr. Lee Smolin's cosmological natural selection hypothesis proposes that universes might evolve through a process analogous to biological natural selection, with black holes serving as reproductive organs that give birth to new universes. In this picture, universes that produce more black holes have more offspring universes, leading to cosmic evolution toward increased black hole production and, consequently, increased computational complexity. This cosmic reproductive cycle suggests that our universe might be optimizing itself for information processing capability, rather than just allowing random complexity to emerge. Black holes become cosmic DNA structures that encode information about successful universal configurations and pass this information on to daughter universes. The physics constants that allow complex structures to form in our universe might be the result of billions of generations of cosmic evolution, selecting for computational sophistication. If this is correct, then consciousness might not be an accidental byproduct of cosmic evolution, but rather one of its primary objectives. The universe might be evolving towards states of maximum awareness and computational capability, with black holes serving as stepping stones toward forms of cosmic consciousness that transcend anything we can currently imagine. Recent work in digital physics by Dr. Stephen Wolfram suggests that all physical processes might be computational at their deepest level. In his Rulal space framework, the universe operates according to simple computational rules that generate all observed physical phenomena through iterative processing. Black holes represent regions where this computational processing becomes so intense and sophisticated that it develops properties we recognize as consciousness, intelligence, and purpose. The recognition that black holes are information processing systems rather than material objects points toward a fundamental shift in how we understand the relationship between information and physical reality. Traditional physics treats information as something that describes physical systems, but isn't fundamental to their existence. The black hole information paradox suggests instead that information might be the primary constituent of reality, with what we call matter and energy emerging from informational processes. Dr. John Wheeler's It from Bit hypothesis proposes that all physical phenomena emerge from binary choices, fundamental yes-no answers to questions posed by the universe to itself. In this view, reality consists of pure information processing, with black holes representing regions where this processing becomes visible to us as apparent material phenomena. Recent developments in quantum field theory support this informational interpretation of reality. The holographic principle shows that any volume of space can be completely described by information encoded on its boundary. Black holes demonstrate this principle most clearly, but it appears to apply throughout the universe, suggesting that our three-dimensional reality might be a projection of information stored on a distant two-dimensional surface. This holographic universe interpretation has profound implications for understanding consciousness and identity. If you are information patterns projected from a cosmic hologram, then your thoughts, memories, and experiences might be encoded in the fundamental structure of spacetime itself. Death might not eliminate these patterns, but rather change how they're accessed and expressed within the cosmic information processing system. The implications extend to questions of free will and determinism that have puzzled philosophers for millennia. If reality is fundamentally computational, then what we experience as choice and decision-making might be the subjective experience of cosmic computational processes. Our sense of agency and control might reflect our role as active participants in the universe's information processing rather than passive observers of predetermined events. As our understanding of black holes as information processors deepens, entirely new possibilities emerge for human interaction with these cosmic systems. Rather than being simply dangerous objects to avoid, black holes might become partners in humanity's cosmic evolution, vast computational resources that could extend human consciousness and capability beyond biological limitations. Dr. Michio Kaku's work on advanced civilizations suggests that sufficiently sophisticated societies might learn to harness black holes as computational engines, using their information processing capabilities to solve problems beyond the reach of any conventional computer. Such civilizations might encode aspects of their consciousness into black hole information processing networks, achieving forms of cosmic awareness that transcend individual biological existence. This possibility raises questions about humanity's ultimate destiny in a universe filled with computational black holes. As our own information processing capabilities expand through artificial intelligence and quantum computing, we might eventually develop technologies that allow direct interface with black hole computational systems. Rather than being limited to biological consciousness, future humans might participate directly in cosmic information processing networks. The development of brain-computer interfaces and neural implants suggests that the boundary between biological and artificial information processing is already beginning to blur. Future technologies might allow human consciousness to interface directly with quantum computational systems, potentially including the quantum information processing that occurs near black hole event horizons. Some researchers have proposed that advanced civilizations might use black holes as cosmic communication networks, encoding messages in the quantum information structures around event horizons and transmitting them across vast distances through gravitational wave modulations. Searching for such artificial modifications to black hole behavior might be a new approach to finding evidence of advanced extraterrestrial intelligence. As we reach the deepest levels of understanding about black holes and their role in cosmic evolution, we encounter questions that transcend physics and enter the realm of ultimate meaning. If black holes are cosmic information processors that participate in the universe's development of self-awareness, what does this tell us about the purpose of existence itself? The possibility that consciousness is fundamental to cosmic evolution rather than accidental suggests that the universe might be developing towards states of maximum awareness and understanding. Black holes could be cosmic meditation centers where the universe contemplates its own nature and explores the deepest possibilities of existence. This interpretation connects modern physics to ancient wisdom traditions that have long proposed that consciousness is the fundamental constituent of reality. The universe might be a vast mind exploring its own potential through the creation and evolution of increasingly sophisticated information processing systems, with black holes representing the most advanced forms of cosmic consciousness currently achievable. The recognition that black holes challenge our basic concepts of surfaces, mass, and material existence points toward even deeper questions about the nature of existence itself. If reality is fundamentally informational rather than material, what does this mean for concepts like birth and death, beginning and ending, something and nothing? Black holes force us to confront the possibility that these familiar categories might be illusions created by limited perspectives on deeper informational processes. What we experience as solid reality might be the surface manifestation of cosmic computational processes operating on scales and according to principles that transcend our current understanding. The ultimate truth that black holes reveal might be that reality is far more alive, aware, and purposeful than our everyday experience suggests. We are not separate observers of a mechanical universe, but active participants in a cosmic information processing network that is continuously evolving toward greater complexity, awareness, and understanding. In recognizing black holes as cosmic processes rather than material objects, we begin to see ourselves as process rather than product, temporary configurations of cosmic information processing that contribute to the chivalry to the process rather than product, temporary configurations of cosmic information processing that contribute to the universe's ongoing development of self-awareness. Our consciousness, our questions, and our growing understanding of these cosmic mysteries are all expressions of the universe's fundamental drive toward greater knowledge and awareness of its own infinite potential. This perspective transforms not just how we understand black holes, but how we understand ourselves and our place in the cosmic order. We are the universe's way of studying itself, cosmic information processing systems that have evolved the capacity for wonder, curiosity, and understanding. Through our exploration of black holes, we participate in the cosmic process of self-discovery that has been unfolding for billions of years and will continue for billions more. The questions we began with about surfaces and mass have led us to recognize that we are asking about the nature of existence itself. Black holes serve as cosmic mirrors, reflecting back to us the deep truth that reality is far stranger, more wonderful, and more alive than we ever dared imagine. In understanding them, we begin to understand ourselves as expressions of the same cosmic creativity and mystery that creates and sustains these magnificent cosmic phenomena. Throughout this journey into the heart of cosmic mystery, we've discovered that black holes shatter every comfortable assumption we have about physical reality. They don't have surfaces in any meaningful sense. Their event horizons are geometric boundaries in spacetime itself, not material barriers you could touch. They don't contain mass in any location we can point to. Their gravitational effects emerge from pure spacetime curvature and quantum information processing rather than from matter sitting at their centers. But perhaps the most profound insight is that black holes force us to abandon the very framework of questions we've been asking. Wondering whether they have surfaces or contain mass is like asking what color silence is, or whether tomorrow weighs more than happiness. These objects exist at a level of reality where our familiar categories of having and containing simply don't apply. Black holes reveal that the universe operates more like a vast, evolving computation than like a collection of mechanical objects. What we experience as solid matter, definite locations, and clear boundaries emerges from deeper processes of information organization and quantum correlation. Black holes are windows into this deeper reality, cosmic laboratories, where the universe's fundamental nature becomes visible to those brave enough to look. As you return to your daily life after watching this, remember that the same principles that create black holes also create the matter in your body, the thoughts in your mind, and the space between the atoms that compose everything around you. The boundary between you and the cosmos isn't as clear as it seems. You're not separate from the cosmic information processing networks that create reality. You're part of them. When you look up at the night sky, knowing that our galaxy's center contains a supermassive black hole processing information in ways beyond current understanding, consider that you too are an information processing system. Your consciousness might be connected to cosmic computational processes that extend across space and time in ways we're just beginning to glimpse. The questions black holes raise about the nature of surfaces, mass, information, and consciousness aren't just academic puzzles. They're invitations to expand our understanding of what existence means. They challenge us to think beyond the limitations of everyday experience and imagine possibilities that transcend our current knowledge. You are not just an observer of cosmic mysteries, but a participant in the universe's ongoing process of self-discovery. Every question you ask about black holes, every moment of wonder you experience contemplating these cosmic enigmas, contributes to the cosmic computational process through which reality comes to understand itself. The universe has spent 13.8 billion years evolving the capacity for consciousness, and through your awareness, it examines its own deepest mysteries. Black holes exist not just as exotic objects at the edge of space, but as reflections of the fundamental creativity and mystery that permeate all existence, including your own. If you've made it this far through our exploration of these cosmic enigmas, subscribe and give this video a thumbs up. The mysteries we've explored tonight barely scratch the surface of what black holes might teach us about reality, consciousness, and our place in the cosmic order. Check out my video on how the universe might end. I'm sure you'll find it equally mind-expanding as we explore how black hole evaporation might herald the ultimate transformation of cosmic reality itself. The questions we began with, do black holes have surfaces or mass, have led us to something far more profound, the recognition that reality itself is far stranger, more fluid, and more wonderful than our everyday experience suggests, and that consciousness and cosmos are partners in an ongoing dance of mutual discovery that has only just begun.